Hello students, let's start with the next topic of our syllabus. That is nothing but what? Change in internal energy of system. So this is the topic that we are going to cover today. Change in internal energy of system. So here, before starting in detail, now here let us consider this is nothing but one of the system we have considered. That means one chamber we have taken. With this chamber, this is nothing but a frictionless, massless pulley, or we can say it is a piston. It is said to be piston. It is movable inside or outside. And within this dot I have shown, these dots are nothing but what? Suppose we have taken any ideal gas. Suppose any gas we have considered. Suppose that is ideal gas. So this ideal gas is nothing but our thermodynamic system, and remaining everything is said to be the environment of the thermodynamic processes. So in this case, while going in detail, first of all, it is very essential to understand the concept. Here we are interested to know change in internal energy of system. For that we have considered the system consists of the gas molecules which are enclosed in a chamber. Chamber has at one end, this is a frictionless, motionless pulley which can move outside or inside here. Now here we can change the internal energy of any system by two methods. The first method that I have explained within these two diagrams, the first method is this: just attach one burner to the system. Suppose initially the system has a temperature 100 degrees Celsius. So when we start heating it, just apply the burner flame and just try to heat this gas. As we started heating the gas, what will occur? The temperature of the gas get changed. Temperature of gas get changed. That means what? The internal energy get increased. See, 100 degrees Celsius initially. When we heat this gas, heat this system, temperature or heat is transferred to the system, and that's why the temperature becomes increases to 200 degrees Celsius. And now here temperature increases 200 degrees Celsius means what? This gas molecule, whatever with the system, our system got what? Internal energy. Its internal energy changes. So this is the first method to change the internal energy of the system. Apart from this, what is the second method? In second method, this is the second method, I have drawn it here. So suppose initially piston is here, and these are nothing but what? Our system, that is the gas molecules we have. Now here initially the pulley is here. When we push the pulley, compress it, just move the pulley inside. When we move the pulley inside from this position, this dotted position to this position, pulley comes. Now here, as pulley get compressed, what will occur? It will exert a work on the gas molecule, and that will increase the internal energy of the gases. So what we have done, we have compressed the gas. Just press the pulley, so volume get decreased. There is compression of the gas, and due to that compression in the gas, the resultant internal energy of gas can increase here. So these are the two methods by using which we can change the internal energy of any system can be measured. Can be changed either by heating the system or by compressing that system. So these are the two methods. From this experiment, what we can conclude? This experiment conclude the basic experimentation. This experimentation conclude the formulation of first law of thermodynamics. How the first law of thermodynamics will do, that is nothing but a conclusion of this. So let's start with the first law of thermodynamics. So next part of our topic is what? We are going to start the first law of thermodynamics. To start with the first law of thermodynamics, let us consider the system as I have shown it here. So we are going to start the first law of thermodynamics. So I will write here first law of thermodynamics. First law of thermodynamics. So what exactly this law is that we have to learn, and for this initially we have just seen change in internal energy. That is again the part of this same. So let's start with the system here. So again these are the molecules of the gas which are enclosed in a chamber, and this is the piston. So this is a piston which is movable along this system. Now in this system there are two things. As system can do the work, or this gas can exert a pressure, gas molecule exert a pressure on the piston, so the piston gets shifted to this side. Move outside means what? There is a expansion of the gas. So this is the first thing. And second thing, if this gas molecule can't exert a force on the piston exert a force on the gas molecule, so piston moves inside. So that is another thing. So these are the two things, how the piston can move inside by compression, piston can move outside by expansion. So these are the two concepts here. So here start with this. The first one, the gas does a positive work on a piston when piston moves outside. piston moves outside, so this gas molecule exert a pressure on it and they will do the positive work. Opposite to this, if the piston move inside, the gas molecule exert the negative work because they are compressed. So that is nothing but a negative work done by the gas molecule. Apart from this, just if you see the same system, nothing but what I have shown it here in this diagram. If you consider this same system is here, and this A is the area, suppose area of the cylinder A, and suppose I want to move this cylinder, this is a pulley, this pulley having area A, I want to move it by distance dx. So there must be the work done. And before going to the work done, first of all we know the equation for pressure. So what is the equation for pressure? So pressure equal to force divided by area. So this implies that force equal to pressure into area. So let us consider the area of this piston is A. So the pressure exerted is nothing but a force exerted is nothing but a pressure into area, that I have shown it here. So that was derived from this equation. Now for further small displacement of a piston by a distance dx, we have to do some work done, and that work done can be written as dw equal to force into displacement is dx. Force is F, displacement is dx. Put the value of force, so we can write force is nothing but a pressure into area into displacement. Area into displacement gives the volume. So what we get here? So work done equal to pressure into volume. So this is the work done, dw required for a displacement of piston by an amount dx. The work done required is this much. Now let us consider here one parameter. That parameter is what? Let us suppose initial volume. Before initially here it is a piston, na? So its initial volume is suppose Vi, and after expansion here when this piston comes here, the volume is suppose Vf. So total work done required to change the volume of system from Vi to Vf can be find out by integrating this equation. So integrate this equation. So integration of dw, here volume of the system varies from Vi to Vf. So you can write this as integration of dw is what? Total work done, that was represented by W, equal to Pdv. It comes to be integration of Pdv. We want to find out. P is a constant, take it outside. Integration of dv is V. So P into V, upper limit Vf, lower limit Vi. Same thing can be written as, if we solve it further, same thing can be written in terms of the another parameter. So just put upper limit minus lower limit. You can write this as is equal to P into upper limit Vf minus Vi, and that will give the work done required to change the volume of a system. This much work done is required. W equal to P into Vf minus Vi. This much work done is required, okay, to change the volume of a system from Vi to Vf. Now apart from this is not again a mathematical statement. This is not a mathematical statement of first law of thermodynamics. Now what the first law of thermodynamics is, for example, initially suppose I have applied some force on it. Suppose initially I have applied some I have added some energy Q to the system, so that system does not do any work. This system is here, and I have added here in this system, I have added the amount of energy, Q amount of energy supplied to the system, and such that system will not perform any work. Then how this energy is utilized? This amount of energy supplied to the system is used to increase its internal energy. And if the internal energy of system get increased, we can write here simple equation, that is when amount of energy Q is supplied to the system, it is used to increase the internal energy of system. So we know internal energy was represented by delta U. You can write delta U equal to amount of energy supplied. That is equation 1 we get. That means amount of energy supplied to system and it does not do any work, then this energy is used to increase the internal energy of system. So delta U equal to Q you can write. Suppose in the next step, suppose amount of energy Q is supplied to the system, and that amount of energy Q supplied to system is totally used to perform a work done. is used total amount of energy here supplied to system is either used to increase the internal energy, first case. Second case, if it is it does not increase the internal energy, to whole energy supplied is used to perform a work done, then what we can write? Then you can write here the amount of energy supplied to the system is used to do the work done, and that's why the internal energy get decreases, and that is equal to minus of W, because that work done, whole energy is used in work done, that's why it comes to be minus. And here finally you can write one thing. Suppose some part of energy is used to increase the internal energy, some part is used to increase the to perform a work done, then you can write the total energy supplied can be written as Q equal to amount of energy supplied to the system can be partly used to increase internal energy and partly used to do the work done. Now here this equation is nothing but a mathematical statement of first law of thermodynamics, which says that amount of energy supplied to the system is used, some part of energy is used to increase the internal energy and remaining part is used to do the work done. So this is nothing but a mathematical statement of first law of thermodynamics. Now here, apart from this, in the same topic little bit they have increased the complication further. So they have what they have done on next page, this figure 4.8a, B and C, these three figures they have taken. What they have tried to explain in these three figures, they just try to explain simple concept. What will occur if the internal energy get increased? Internal energy get increased in first case. Second case, internal energy decreases. Third case, there is no change in internal energy. So these three things they just try to explain it here. And after that figure 4.8c, they have just given here most important parameter. This first law of thermodynamics is in consequences with, or it is a generalization of law of conservation of energy. So this first law of thermodynamics is also said to be law of conservation of energy because it is consequences of or generalization of law of conservation of energy. So apart from this, the next topic of the syllabus is nothing but what? Thermodynamic state variables. What are the variables used in thermodynamic states? So that variables we have to learn. So that variables we have to see. Variables in thermodynamic state. So that variables we have to learn before going in detail of the process. So let's start with thermodynamic state variable. So it is thermodynamic state variable. Variables. So what are the thermodynamic state variables? So these are nothing but the quantities in the system. So whenever we consider thermodynamic system and environment, there are some quantities which are changing, and that changing quantities are considered as a variable. As we know in mathematics, x and y and z are said to be variable. Similarly here in this thermodynamic system, some quantities which are changes that are said to be the variables. What are the quantities that are changes? So we know the pressure of the gas, volume of the gas, temperature of the gas, density of the gas, mass of the gas, all these parameters are changing. These parameters are changing in the system, and that are nothing but what? They are considered as thermodynamic state variables. Now basically there are two type of state variables in thermodynamics. One is said to be intensive. So first said to be intensive variable, and second is said to be extensive variable. So what exactly the difference between these two? So first is said to be intensive variable, second is said to be extensive variable. Intensive variables are the variables which does not depend on size of system. So intensive variable does not depend on size of system. Okay, and while extensive variable depend on size of system. Now it is a little bit confusing. How can we distinguish? So intensive variable are the variable which does not depend on size of the system. Whatever be the size, the variable remains same. The extensive variables are the variable which depend on size of system. If system is large, then the variable get different. If system size get decreased, the value of variable get changed. So that is nothing but this parameter. So here we are here. So thermodynamic state variables we have seen. The parameter will get changes in a system that are said to be thermodynamic state variables that we have already learned. Now there are two types, in intensive variable and extensive variable. Intensive variables are the variable which does not depend on size. Size of system get increase or decrease, still this variable remains same. So that are said to be intensive variable. And extensive variables are the variable in thermodynamic system. If the size of system get changed, then this variable get changed. And so these are said to be extensive variable. Now here let's start with one of the best example. Suppose initially we have taken some gas. So suppose this is a chamber. In this chamber any gas we have taken. Suppose some amount of gas we have taken in this chamber. Now what are the variables in this? In these variables are nothing but this. All these things are the variables. Pressure, volume, temperature, density, mass. These are the variable in this system. Now what we have done? We have break this whole system. This is a bigger system we have taken, suppose. Now I have just divided this system into two equal parts. So suppose whole system is divided equally into two equal parts. So here I have just made divider. Now this is a division. The two systems get separated now. Single system converted into two systems of equal parts. Now what get occurred with the here? To this, suppose this is a first system, this is a second system. In first and second system, in this case, initially which is the same one initially. Now we have split it into two parts, 1 and 2. In this both system 1 and 2, pressure, volume, temperature, density of the same gas remains same. So this parameter which remains same before and after division of the system comes under this intensive variable, because in this case size get changed, the variable remains same. So that is the intensive variable. But as we have divided equally into two parts, initially suppose the mass of the gas is m. Now whole system divided into two equal parts. So this mass is what? M by 2, and this mass is again M by 2. What will occur with the variable? Initially variable is M, now it is M by 2. Variable get changed, and such a variable which get changed with the size, they are said to be extensive variable. So these are the two type of variables that we have to learn. Now let's go to next one. That next parameter is what? Thermodynamic equilibrium. So thermodynamic equilibrium, if you remember, when we start this chapter initially, before learning the 0th law of thermodynamics, we have seen the equilibrium. So when the two systems or two or more than two bodies are at equal temperature, they are said to be in thermal equilibrium. So that here we have to say thermodynamic equilibrium. Now there are three types of thermodynamic equilibrium. The first is mechanical equilibrium. So it is a mechanical equilibrium. So what exactly mechanical equilibrium? It is one of the type of thermodynamic equilibrium. Mechanical equilibrium is equilibrium when there are no unbalanced forces within the system and between the system and surrounding. There is no any unbalanced force within the system and surrounding. There is no any unbalanced force acting on that system. Then that systems are said to be under mechanical equilibrium. So they are at a mechanical equilibrium because there is no any unbalanced force. Or in short, we can say another way, pressure throughout the system and outside the system remains constant. Pressure inside and outside the system remains same. It will never get changed throughout the whole process. If the pressure is constant, we can say system is said to be in mechanical equilibrium. Second parameter is what? Chemical equilibrium. So let's start with this chemical. So chemical equilibrium, and third one is nothing but what they have mentioned, third one, thermal equilibrium. So these are the three types of thermodynamic equilibrium. So we have learned this mechanical. Now let's go to chemical. Chemical equilibrium says that throughout the thermodynamic process, if there is no any chemical reactions going to carry out, chemical reaction is not there. So throughout the process of thermodynamics, there is no chemical reaction, or we can say there is no change in a composition of system. There is no change in composition. So change in composition can occur whenever there is some chemical reaction is going on. If there is no chemical reaction, there should not be change in the composition of system. So whatever system we have taken initially, it remains as it is throughout the process because there is no any chemical change. Then that type of equilibrium is said to be chemical equilibrium. And third one is said to be thermal equilibrium. Thermal equilibrium is what? This thermal equilibrium is an equilibrium where throughout the thermodynamic process temperature remains constant. As it is thermal, so temperature throughout the process is same, it never gets changed, then that type of equilibrium is said to be thermal equilibrium. So these are nothing but what thermal equilibriums we have seen, and the variable of thermodynamic system and processes that we have seen. Now next topic is what? Thermodynamic state variables and equation of state. Equation of state, we know PV equal to nRT. That equation of state we have to see, and what is the relation with the thermodynamic variable, that we have to see in this process. So that topic we'll see in the next video. Okay, so just try to watch my video. After watching, try to understand it and read the same topic from your book for your better understanding. So take care. We will see in next video with thermodynamic state variable and equation of state. Thank you.